Les recordamos que al finalizar cada conferencia, los estudiantes pasarán recogiendo los formatos de preguntas que se les entregó junto con el material de registro. Orden de la sesión. Conferencia a cargo de Annie Pierce, PhD de la Universidad de Georgia Institute of Technology y profesora asociada de la Escuela de Construcción en la Universidad de Virginia Tech. Conferencia a cargo de Houston Eubank, consultor en el área de sostenibilidad para edificios y comunidades, especialista senior Fulbright y fundador del World Building Council. Panel de preguntas liderado por el profesor Hernando Vargas, máster de la Universidad de Massachusetts Institute of Technology y profesor asociado del Departamento de Ingeniería Civil y Arquitectura de la Universidad de los Andes. Por motivos de fuerza mayor, Cristian Rada no nos puede acompañar. Conferencia a cargo de Annie Pierce, PhD de la Universidad de Georgia Institute of Technology y profesora asociada de la Escuela de Construcción en la Universidad de Virginia Tech.
Buenos días. Well, so I am a professor, and imagine my delight when I learned that I would have more time to talk with you than I had planned. So, today I'm going to speak with you about lessons learned when implementing sustainability. So I call this talk Evolution of the Built Environment Using Sustainability Innovations. And what I have on the slide is a picture of a field, because that's where a lot of our lessons happen. And that is what I study as a professor. So sustainability has been around quite a while. This is the timeline of development for measurement systems for sustainability. You've heard about some of these already, but you can see as far back as 1990, we were developing tools and techniques that could help us implement ideas from sustainability as part of our built environment. I was lucky enough to get involved with sustainable engineering back in the 90s. Some of you know this gentleman up here. This is Dr. Jorge Vanegas, and I'm delighted to be speaking here at his alma mater. Dr. Vanegas was my doctoral advisor at Georgia Tech, and so I learned quite a bit about sustainability from him. And he was pivotal in bringing sustainable engineering to the curriculum at Georgia Tech. And the provost at the time really captured it well, I think, when he said that sustainability is about changing our mindsets, not just our problem sets. It really requires approaching problems in a fundamentally different way than we have in the past. So at Georgia Tech, we did a lot of interesting research, and I'm going to show you this figure and another one on the next slide that will probably make your head hurt, give you a headache. The point is not necessarily the figures, but the idea that we approached sustainability in the 90s just as we would any other kind of research topic. We looked at it from the standpoint of optimization. And so the figure that you see on this slide is about supporting optimal decision-making for renovation using sustainability principles. And so this was some of the early work that happened in that area. So hold on to your hat. Here's the next figure. This one, again, took the idea a little bit further. And so at Georgia Tech in the 90s, we were looking at theoretical sustainability. And we had a lot of ideas about how practice should change and how you could apply cutting-edge research to achieving sustainability. So I finished my PhD in 1999 and went on to start focusing on taking sustainability ideas into practice. Some of the research that we did at Georgia Tech was important, but it didn't exist outside the laboratory. And so I was fortunate to be able to participate as part of the development of a professional training series on sustainability. So this was a little bit ahead of its time, but it was taught all around the US and also in other countries around the world. And interesting thing, but what it was really all about was taking research from the laboratory out to the real decision makers in the streets. And so starting in 2000, I spent a lot of my time in front of people like these, talking about theoretical sustainability. And I showed them pictures like the slides I showed you a moment ago, great ideas from a theoretical standpoint, but not necessarily as easy to implement as these people would want. And so I became aware, after working in this field for approaching 10 years, that sustainability really is less about technology and, in my opinion, more about people. And so, in fact, my experiences in teaching sustainability to practicing professionals has influenced the rest of my career since then. And so I spend my time studying people like her and trying to understand what it is that motivates people like that lady there. And specifically, I study government employees in the US. And I try to understand how to get them to change their behavior when they're making decisions about the built environment. And what I have learned in my research, I'm going to share with you today a little bit about what the constraints are that they face and what motivates people to change. And then I'll also share with you some experiences that we're learning now in the US about things that can go wrong with sustainability if you're not careful. So my goal as a professional now is to avoid people looking at me like that when I speak to them about sustainability. So over the past 20-odd years of working in this field, I've had the occasion to go out and visit many projects. And one of the things I find very interesting is how they fail, how they go wrong when you attempt to implement technologies that are not necessarily a good fit for the situation. And so I collect stories about what is not sustainable. So for example, what you see on the slide here is an example of a fuel cell power production module that was installed on a government Air Force base, actually in Minnesota. And it's basically a giant metal box that's sitting there and not being used. And at the time that I took this picture, the reason it wasn't being used is that natural gas prices in the US had fluctuated wildly, and it was less economical to produce power with this technology than to purchase it from the grid. And this, I should mention, this fuel cell was provided at no cost to the government installation through a grant program. So although that box right there at the time cost about $1 million US, there it sat as a giant metal sculpture, a testament to a bad decision. Here's another example. This is a picture of part of an experimental building that my students at Georgia Tech constructed back in the 1990s. Many of you may be aware of the early efforts to make buildings more green, more sustainable. This is a picture of what still is called an earthship wall, made from waste tires and compressed soil. Very strong building material. It makes use of a waste stream instead of some sort of virgin resources to construct the wall, but not necessarily something that people would necessarily want to have their buildings made from. And so often in the early days of sustainability, when you would talk with somebody about making your building more sustainable, this is what they'd think about, because many of those early examples were that extreme. And so what we learned over the long run is that buildings must be competitive with what alternatives people have in the marketplace. So if you want to make a building that's truly sustainable, you have to make one that people will actually want to use because they have options that they can choose from. So it has to be competitive in the marketplace. Here's another example of a technology on a government installation in the US. This one, I don't know if you can see it very well. It's a passive solar hot water heating array, and it was installed at a national park visitor center in Colorado. So that was its initial purpose. Again, now like the fuel cell, it's a sculpture. It basically sits there. It was decommissioned after 1 year of use and replaced with a more conventional electric resistance water heating system that was more familiar to the people who were responsible for maintaining the building. So this is an example of a technology that was a poor fit for the context in which it was implemented. And last but not least, this is a picture of a building that is on a college campus. It's actually a picture of the College of Architecture. So I haven't had the pleasure of visiting the Department of Architecture here. I trust you have no examples of user modification in your building, but at least in the US, many of the architecture buildings I walk into are living laboratories for how people need to adjust the environment to fit their needs. And this is also an artifact of buildings evolving over time to meet different kinds of use requirements. So buildings have a long lifespan. Rarely when we construct them do we know what needs they will fulfill. This particular door opened onto a major circulation path in the college. It started out as a door to a mailroom, and because of lack of space, eventually it was repurposed as an office. But it did not work well at all as an office because of acoustics. And so the people who were assigned to that space went back and had to modify the design features in order to make it work for them. So in constructing our buildings, in constructing sustainable buildings, we have to be aware not only of the economic context in which our buildings will operate, of the market competition we have for people who are making choices of where to locate. We have to be aware of the kind of ongoing responsibility that our buildings will require. And lastly, we have to be able to anticipate what our user needs are going to be. Otherwise, we end up with a building that may be more environmentally friendly, but is ultimately not used to its capacity, and therefore not a good use of resources. So I also spend some time trying to understand what does work and why. And the data in this graph is not necessarily as important as understanding that it's important to know what priorities are of people who will be responsible for implementing your building. So this data is from 2002, and it was taken from a series of military installations in the US where people identified what their most preferred green technologies were for use in their projects. And it was based on the LEED Green Building Rating System at the time. And so when we went out and trained people, we asked them to vote on which technologies they thought would be most implementable. And these are the winners. Okay, so if I took the same poll in a private sector organization, in a house, we heard earlier about sustainable home construction, would I get a different answer? I probably would. So my point with this graph is that you have to be aware of context in understanding what technologies are most likely to work. In thinking about people who adopt sustainability, it's important to understand that we have different characteristics as decision makers, as well as different priorities. So we all know somebody, maybe it's you, maybe it's a friend or family member. We all know somebody who has to be the first person to have the next new technology. And so this graph shows an example of those people. Those are the innovators down here. This is time along the x-axis, and you can see that as a new technology or innovation enters the marketplace, it's initially picked up by people who like new things just because they're new. They can see the potential benefits without necessarily having to have proof that those benefits exist. Over time, technologies become more broadly adopted in the marketplace, and we eventually, for innovations that are successful, eventually reach a peak where at least half of the market has taken up the new technology. There are still people out here who may wait until they absolutely cannot avoid new technology to adopt them. But understanding the characteristics of the population that you're trying to persuade is extremely important. So I want you to remember the shape of this graph. This is a normal distribution. It's a bell curve, and we see this quite a bit. So I'll show you some other examples. Here, for example, is an industry trend in U.S. Green Building Council membership from 1996, when it was originally put together, through the year 2006. And you see that same increase here, working up the curve. Likewise, if we look at the U.S. and LEED certified projects, we see the same kind of shape. You start small, innovators take up the innovation, and eventually it becomes more and more mainstream. So I'll ask you this, both these graphs end in 2006. That's 10 years ago. Where do you think we are today? Have we continued up the curve? Have we hit the peak? Well, this is an example of annual registrations of LEED projects for new construction. And when you look at these data, you see that those registrations peaked in 2009. So if you think about what happened in 2009, you may remember that in the US anyway, we had a very serious economic depression period. The construction industry backed off quite a bit. But we also saw at that point a difference in the kinds of motivations that people may have for implementing a rating system. So whereas early on, there were many policies in place that mandated implementation of the LEED rating system, as new systems entered the market, those policies became more flexible. People were able to choose different rating systems. We also saw policies emerge where rating systems became optional. You had to build your structure so that it could meet LEED requirements, but you didn't necessarily have to pay for certification. So these kinds of trends are important in understanding who our audience is for green innovations. So one thing that's interesting to note is that often we see what's called Moore's chasm in that advance of technologies. This is a theory that looks at why good ideas sometimes stall and fail to take off. We have seen green building advance in the U.S. marketplace, but we are not yet to a point where the majority of buildings are certified. So this shape that we saw back here is not necessarily having reached that peak yet. Something else is happening. So what is that? Well, Moore's chasm is one way to understand what's going on. So this theory was developed as a response to the dot-com industry, the computing industry, in which we had tremendous market investment in innovations, and we would have companies develop an innovation, attempt to go public with that innovation, and convert their company to a publicly owned company. And we would see tremendous investment in ideas. And then not long after that, the companies would all of a sudden start not to do so well. And so we became curious whether this was something that we could observe in the green industry as well. And so to understand why this happens, you have to understand that the characteristics of each of those groups are important in understanding people's motivations. So here again is the innovation diffusion curve. Again, you see the bell shape, and you see the major categories here between these innovators and early adopters through the majority and down through the laggards at the end. What's important to realize is that the kind of evidence that will persuade these people is very different than the kind of evidence required down here. And that's extremely important in motivating the diffusion and adoption of an innovation. So the people at the top end of the curve here, they're willing to take a risk. The next category, early adopters, they're also willing to take a risk, but they like to hear the stories of their friends that maybe took the risk first. But in any event, both of these categories are willing to risk the potential pitfalls of adopting a new technology without necessarily seeing solid evidence about costs and benefits. On the other hand, downstream, these adopter categories need solid evidence. The early majority may not want to see formal research studies, but they still require anecdotal evidence. The late majority and laggards will not voluntarily adopt an innovation until there is proof out there, and in some cases, incontrovertible proof, that what they will adopt will be successful for them. So what we have to understand from this is that as we approach a majority of people considering sustainable construction in a marketplace, we have to be able to prove to those people that it's actually going to work for them. So one of the ways we understand this is by studying a concept called routinization. I have no idea how that translates in Spanish, but in any event, so we started to study routinization. Routinization is the idea that you will try a technology, and if it has a good outcome, you will continue to use that technology in subsequent projects. We know this is how design is often done. We know this is how construction often happens. And so we wanted to understand what factors caused some technologies to be routinized and others not. And so we looked at 3 different factors, and I'm going to show you a little bit about what we found with these. So the first factor is how radical the change is. So if you think about this, I'm going to ask you to imagine in your mind which of these you might be more likely to decide to try. The radical innovation or the incremental innovation. So we defined incremental innovation as technologies that don't require any changes in complementary systems. Maybe they're just a different kind of the same system. And they can be implemented without any particular kind of expertise by existing construction stakeholders. So an example of this are the 3 different types of light bulbs, lamps that you see there. These have Edison bases. They fit in standard fixtures, at least in the US. And so if you wanted to adopt this, it would be as easy as removing your old lamp and putting the new one in. No change in supporting systems required. Radical innovations, on the other hand, require changes in complementary systems. They may require introduction of completely new systems. And often they require the people who implement, the contractors, to behave in ways they're not used to behaving. And so here you see an example of photovoltaic panels. These are being installed by electricians who are not necessarily used to having to work safely at height. So in order for people to install technology such as this, they have to learn how to use fall protection. And these are skills that are outside what they need to do. So not only is the technology different, but it requires a fundamental change in how you operate and the conditions in which you operate. So think about it. Which one do you think is more likely to be routinized? That is, used again and again and again. Here's what we found. Okay, so we looked at public sector stakeholders that had multiple buildings in their portfolios, and we saw pretty clearly that the technologies they repeatedly implemented in their projects tended to be incremental instead of radical. So in this plot, you'll see that the green bars are the incremental innovations, and the blue bars are the radical innovations. Not especially surprising, right? So let's look at the next category. The next idea that we looked at was product versus process change. So if you want to innovate for a product innovation, basically you may be able to just purchase that technology without requiring any changes in your operational conditions following adoption. So an example here is OLED lighting. This doesn't require any new kinds of actions on the part of people maintaining the project. In fact, it requires less because the life of this technology is longer. A process change, on the other hand, requires changes to owner behavior or expectations. And it requires different operating conditions than people are used to. And so I included here an example of what once was a green wall, a vegetative wall, that was part of a space that went into This was from a corporate facility in South Korea where the building was built as an experimental building, and subsequently the company that developed it moved people out of the office and shut the building down temporarily. Most systems we use in our buildings can survive okay. They can survive just fine when you leave and lock the doors. Not so your vegetated technologies like living walls. And so that's an example of a technology that required a change in the operational procedures of that company and failed when it did not achieve that change. So think about it. Which one do you think is going to win? Product or process? Maybe you're not surprised to see that product changes were the most frequently routinized. It's a lot easier for organizations to make changes where they can swap things in and out, again, without having to change their behavior. All right, last but not least, we looked at direct versus indirect economic benefits in what owner organizations decided to implement. So direct benefits come from technologies where there is a positive cash flow or measurable savings that accrue to the owner, the person who chooses to implement these technologies. So in order for an innovation to be rated as having direct benefits, it had to have some measurable, likely economic benefit to the owner. And so the example here is low VOC paint. And you saw earlier that that was one of the most popular green technologies we found to be adopted in government organizations. And this offers direct economic benefits to owners because not only is it roughly equivalent in price to conventional paint, but it allows activities to resume more quickly in occupied spaces. So you have less downtime, which means that your productivity can resume more quickly. So that's a product with a direct economic benefit. Indirect benefits, on the other hand, might offer some kind of cash flow or savings in very specific contexts, but not all the time. They may also offer benefits to society at large. So the example I have here is floor tile with recycled content made from windshield glass. This is a technology that was implemented in my office building at Virginia Tech. And so this is a product that was much more expensive than conventional porcelain tile that you would use in an application like this one. It had a much higher initial cost and offered no savings over the product it displaced. It has environmental benefits because it uses a waste stream. It also has public relations benefits if you understand the environmental benefits that it offers, but no direct payback to the owner. So which of these do you think is more important? Actually, what we found here was less conclusive. And I have to say, we still found this kind of surprising in that it was very inconsistent. And so what we discovered in our studies of institutional owners is that, first of all, this is a context in which experimentation may occur with technologies that have a good organizational fit, even if they don't necessarily have that direct benefit. And so this is an area that we continue to study. We know that economics drives a lot of decision making, but we have yet to find exactly what that magic formula is. So what does all this mean for you? How does it affect what you do in your practice? So what I study now are these kinds of questions. I'm very interested in understanding how we can get human decision makers to make more sustainable choices. I want to understand the factors that drive their decision making. And as an engineer who designs technological systems, I want to understand how I can position and design my technology such that it has a better chance of being adopted and having the desired impacts that it was designed to have. I want to understand what controls that fit between a technology and a context of use. And so ultimately, what I study is how we optimize socio-enviro-technological systems, all three of those factors together simultaneously. So to do this, we have to understand the approach we take now to designing. And I'll speak from the standpoint of an engineer. I can't necessarily capture the thinking that architects do, but from an engineering standpoint, we know how to design. We calculate when failure will occur, and we design to avoid that failure. And nevertheless, we still have situations like this, where bridges collapse. Not because they weren't designed well, but because we made mistakes when we anticipated how they would be maintained, what loads they would be expected to hold. So how do we apply these lessons to sustainable technologies? We need to better understand new kinds of failures. So I'm going to show you some examples of these very specific kinds of failures that we are seeing in sustainable technologies. Here is an example of a sustainable, a green technology cluster where the technologies are complementary, where each has benefits by virtue of being used with the others together. So what we have here is a standing seam commercial metal roof, right here. On top of the metal roof, we have laminated photovoltaics. Not necessarily the most efficient system, but power production taking place on a roof surface. Beneath the roof surface, we have a hot water preheating system where heat absorbed by the roof is used to preheat water that's required for use in the building. How is this synergistic? Well, first of all, we have three technologies being used in the same space, which is something that's quite handy when you're trying to design a facility. But also, we have a synergy that results from the heat transfer from the photovoltaic surface to the water. So the water actually acts as a cooling mechanism for the photovoltaic panels. You may or may not know that photovoltaic panels have an optimal production at a specific temperature. If they get hotter than that temperature, their efficiency drops off. And so by putting a mechanism to help cool the panels beneath those panels, we're able to transfer the heat away from the photovoltaics and into the water where it can do something useful. So this is a synergistic example. And it combines energy production, effective roofing, and a building envelope, and hot water production. This is the kind of synergy we want to achieve. Here's an example of an interaction that we do not want to happen. And so this is, it's a little bit difficult to see here, but this is an innovative kind of concrete form that's used in the United States. It's made from extruded polystyrene, and these giant blocks they're 8 feet long, and you snap them together and it creates a continuous thermal envelope on the inside and outside of your concrete wall. So what you see here is the foam exterior. Behind it is a 6-inch concrete wall, reinforced. And then on the other side is an additional layer of foam. Again, really important when you're trying to achieve a high-performance building envelope. What you see here is an example of a chemical reaction between the sealant that was used on the top slab surface and the polystyrene forms. So this was completely unanticipated in the design of this structure, that chemical interaction. And it actually caused a significant thermal bridge right here because almost all of the concrete form was eroded away. So this is an example of interactions, again, between building systems for insulation, concrete forms, and concrete sealants that was unanticipated. What could possibly go wrong? Well, there are plenty of things that could. And this is an example actually from my house in Virginia. I have an underground rainwater storage system, and I provide all the water for this residence by collecting and harvesting rainwater from the roof. So this is an example of the tanks being installed. So we have here rainwater harvesting, and in the background you can see foundation waterproofing. And again, this is the insulating concrete form system up here that's covered by that. So what could go wrong? Well, this is a very personal example of many, many, many things that could go wrong that are not necessarily as clear as a bad chemical reaction. So this is a case study. Here, I won't go into a lot of detail, but I will assure you that not only do sometimes our innovative technologies interact badly for technical reasons, they also can act poorly together because of management reasons, because of people reasons. So in this project, the tanks were installed under an unusual contract arrangement with unclear schedule responsibility. They were installed on a day when a subcontractor was present with equipment on site, but not active. And so that equipment was mobilized before the tanks arrived on site. And the excavation subcontractor dug the holes too deep. The tank subcontractor decided to use the hole as it was, buried the tanks too deep, left the site after they were installed, but before it was backfilled. And what happened during backfill is that the supply connection to the tanks was ruptured during the backfill process, and nobody knew. All we knew is that the water quality from this system was extremely poor. And you can imagine why that might be happening if you look at the breach in the collection piping here. So all of this long story in this case study shows how many places along the way problems can occur when you're implementing a technology that's unusual. And so you have to understand not only the design factors associated with that technology, but also all the ways in which it will change the construction process as well. I'm going to speak just a little bit more about construction and talk about some of the safety and health risks we are observing in the United States in some of our green projects. So these may or may not have been a factor for you as well, but these are findings from a study commissioned by our National Institutes of Occupational Safety and Health. And this study identified that there are 5 ways in which green buildings are fundamentally different than conventional buildings. And those differences pose potential safety and health risks for the people who build them, the people who occupy them, and the people who maintain them. So if you're like me, when somebody tells you that green buildings might be more dangerous, you're not quite sure what to think, but perhaps you find that surprising. I know I did, but when I started to work on this project and identify those potential risks, I began to see that all of these things are potentially problematic. So I'll show you some examples of these, starting with gravity hazards. And I alluded to this a few slides ago. All of a sudden, by making greater use of the building roof and the building envelope as a platform for doing new things, for providing new functions, we introduce both construction workers and operations and maintenance workers to working at height. And this may not be something that these trades are accustomed to doing. So we now have people who may not be trained. This guy working on a roof has absolutely no fall protection at all. But he's up here installing a photovoltaic integrated roof system. Likewise, vegetated roofs. All wonderful technologies from a design standpoint, but from a construction standpoint, they pose hazards that we as construction managers and designers of construction operations now have to manage and make sure are safe. So by their very nature, green buildings involve doing things on the building envelope that we haven't historically done. The building envelope is now used for more than just enclosure. Now it's a platform for energy production. It may have more glass because it's a platform for lighting. It may hold a stormwater treatment system in the form of a vegetated roof. But all of these things pose new kinds of risks. Mechanical hazards. We expect on our green projects that there will be greater amounts of handling of materials. Not only do we expect additional handling from things like deconstruction, but also things like on-site sorting of recycled materials. All of these things require increased contact with potentially hazardous kinds of materials and systems. We are also introducing new kinds of systems, such as high-performance windows, which you see here, that are inherently heavier than the windows that they're displacing. Now, I know you're not using triple-paned windows here in Columbia all that much, if at all, but these kinds of higher quality building assemblies pose new kinds of risks for the workers that install them. Even if we employ mechanical lifting, now we're introducing new kinds of hazards that may involve risk of crushing or struck by risks. So we have to be aware of these things as we decide what technologies we want to implement. Biological hazards are especially interesting. I'm working with a group at Virginia Tech that is studying potable water systems inside buildings. And we're finding some unanticipated problems with these. One of them has to do with water heating systems. In the US, for example, people are encouraged to reduce the temperature of their water heating system to save energy. What they don't realize is that that creates an ideal temperature for bacteria to breed, including Legionella and other kinds of opportunistic pathogens that can cause problems. So that is an example of a tactic designed to save energy that actually causes a completely new kind of problem that has to be handled. Then we have electrical and temperature hazards. We're incorporating more and more power production systems on our buildings. But what you may not realize is that photovoltaic panels generate a charge every moment that they're exposed to light. So one of the things that has been identified in the US as a hazard for firefighters is that even though you may disconnect your panels when you arrive at a building to address a fire, you can disconnect the panels from the rest of the electrical system. But those panels continue to be live and continue to produce electricity that can harm you, even though they are disconnected. And so we're seeing new ways of fighting fires on green buildings. For example, firefighters might bring a cover and actually cover the surface of photovoltaics to stop that charge production. Completely unanticipated, not what you're thinking about when you install power production on your building. But it poses a real risk, a life-threatening risk to people who have to maintain the building and handle problems. Here's an example of a complex situation where hot water recirculation is used to save energy. In this case, again, we have biological hazards. This is a system that keeps hot water continuously circulating through the system to reduce the amount of water that's wasted at the tap by the user while they wait for water to get warm. And we see the use of this system a lot in areas of the United States where water is very scarce. What we are also seeing in those areas is increased levels of corrosion in the piping due to water constantly cycling through. We see increased temperature mixing in the storage tanks, which lead to possible bacterial issues. We see behavioral issues where people may be less likely to worry about saving energy because they believe that this technology is doing it for them. And so here again, the combination of strategies, all of which have good objectives, can cause increased problems that we don't think about. And here again is my favorite example of water heating. This is a technology that worked perfectly well when it was installed, but because it did not fit the operational practices of its users, it was abandoned in place. So ultimately, I'm interested in creating sustainable, resilient, human-centered communities. And that involves understanding how sustainable technologies work together and what kinds of impacts they have that we may not anticipate when we combine them on the drawing board. Some of the drivers for these things in the US: increased net zero policies, more ambitious design goals. There are also problems with existing infrastructure that are apparent. And we also know that with climate change, there will be increasing stresses put on our infrastructure systems. We know overall that now in 2015, 2016, the green building sector is outpacing construction growth. We finally achieved the peak of that curve in terms of adoption. And we see new technologies being implemented on the construction site to green the supply chain, to improve the efficiency of site operations, to track our carbon footprint, and make sure that we are managing our supply chains to minimize carbon footprints. New kinds of methods and materials. All of these things are improvements. But until we are able to construct buildings that take care of themselves, like this, we are still creating problems. We may be increasing our efficiency. Is that enough? Not necessarily. So this is an example of the Bullitt Center in Seattle, Washington, that was designed to behave like this, to be living, to provide its own water by collecting it from the environment, to treat its own wastewater, to provide all the power that it needs to operate by harvesting it from the sun. So we're starting to fundamentally think differently, fundamentally change our mindsets, not just our technologies. Where do I see us going in the future? One of the things I study now is overall infrastructure networks and how they operate currently and how they might operate in the future. So in understanding the resilience of a human settlement, for example, you might want to design infrastructure that can take advantage of physical characteristics. And obviously this is something we do now when designing our systems, but how can we design infrastructure such that it can operate passively whenever power is cut, for example? So passive survivability is an example of a concept that we consider. Creating our water needs downhill from our water storage. We also want to consider economic characteristics of our markets and look at what happens when privately owned buildings invest in systems that reduce their dependence on centralized infrastructure. How can we plan for the centralized water supply, power production, wastewater treatment? How can we plan those systems while at the same time encouraging private owners to produce their own power, to harvest their own water, to treat their own wastewater? And what should be the balance between those? If you are a government agency that wants to maximize the resilience of a community for which you're responsible, how much should you spend on centralized infrastructure versus incentives and policies to promote distributed infrastructure? Ecological characteristics are also important. For example, in considering a sustainable city, how much of the existing land area should you preserve as a natural ecosystem? And where should you position those in your overall land use to maximize your ability to handle storm events? And lastly, socio-political considerations are also important. When you implement systems that are different from how we have always done things, what changes do we need to make in our organizations to better be able to handle those innovations? How do we need to train people to properly operate them? How do we monitor their behavior? All of these are questions that remain to be answered. So these are some of the key research questions that my team at Virginia Tech is presently studying. I don't know the answers to them, but I believe they're important as we look forward to sustainable communities in the future. I think we need to better understand not only how complex systems behave, but how we as designers, builders, and managers of those systems influence their behavior over time? How can we predict their performance? And how can we use policy to optimize the behavior of the system overall? So what should you conclude from this? If you are a practitioner, maybe you're encouraged, maybe you're discouraged. In my opinion, it's all about finding leverage points. And that's why I spent time today talking about some of the important leverage points that influence people's choices when they are deciding what technologies to adopt and what technologies to routinize. You have to understand the context in which you will apply an innovation before you can expect that innovation to succeed. So it's all about finding those leverage points where a little bit of effort can make a big difference. Sustainability isn't necessarily as easy as it looks. We continue to find new ways in which things can go wrong. But ultimately, if we learn from our mistakes, we can create better buildings, parts of better communities that will enable us to be sustainable in the long run. And with that, I thank you for your attention.